Our second speaker this morning is Elaine Crooks from Swansea University. This is the title.
Okay, so thank you very much, Kewei. So thank you very much also to the organisers for the invitation to speak here. So today I'm going to talk about some work which has been going on over the last few years, and this is in collaboration with Kewei, who is the chair, and with Antonio, who is sitting towards the back. And what I'm going to talk about is compensated convexity, multiscale medial axis maps, and sharp regularity of the distance function. And so I should stress that so many of the key ideas come from Kewei, and many of a great deal of the numerics comes from Antonio, and today I am the messenger. Okay, so so I won't describe these pictures for the moment. I'll tell you a bit about them later on. Okay, so I think I need to do it like this. Okay, so the talk will be in two parts. So I will start off with some fundamental theory background, which is on this idea of compensated convex transforms. And so I will define them and give some very simple examples to show you how they work. And then in particular, talk about a key property that leads us to be able to use them to detect singularities. Okay, so that's a very vague statement, but I'll make it more precise later. And then I'll go on to talk about a specific application. And so, in fact, an application to detecting the so-called medial axis of an object, which I'll describe later, and then talk a little bit about its properties, in particular its stability properties, and show you some examples. Okay, so this is all quite vague, and so let me sort of, without further ado, move on to talking about the details. Okay, so first of all, I'm going to talk about compensated convex transforms, and these arose from work in the calculus of variations in the context of quasi-convex envelopes. And so here is the definition, right? So I will give you the formal definition, and then I will show you what it means for a simple example, so you can see what it is. Okay, so what do we have? Let me see if I can get this to do something. Okay, so we take a function f, which is defined, a real valued function defined on Rn, okay? And then we suppose it has at most quadratic growth at infinity, right? So it could be bounded, but it could grow up to quadratically. And then we take some constant lambda, which is a positive constant, which is a parameter in the problem, okay? And then we define two transforms, right? One is called the lower transform, and the other is called the upper transform. Okay, so let me talk in detail about the lower one, and then the upper one is sort of similar but slightly different. So here's the definition of the lower transform. And so what do we do? So first of all, we take our function f, and then we add on lambda x squared, right? So here this just denotes the usual Euclidean norm. So I take f, I add on lambda x squared, and then we take the convex envelope of that function, right? Where the convex envelope is, as usual, the supremum of all convex functions which lie underneath the function, right? So we take f, we add lambda x squared, we take the convex envelope, and then after that we subtract the lambda x squared off again, okay? Okay, so this is what we do for the lower transform. And then the upper transform is sort of similar but different, right? We take lambda x squared minus f, take the convex envelope, and then we do it the other way around. Okay? Okay, and these were discussed in a paper which Kewei wrote in 2008, published in the Annales de l'Institut Poincaré. And in that paper, a number of, these concepts were introduced, and a number of key properties were derived. And so what I'll do, so first of all, before in a moment, I will sort of show you what these do to a simple function. But before that, let me just sort of make some connections with some other areas, because these are connected to some other concepts. And so there are some alternative characterizations of the upper and lower transforms, which it's important to note, both from the point of view of credit and also from the point of view that sometimes one can use some of these properties to get different proofs of some of our results. But in fact, the original characterization that I gave on the first slide, gives us the sort of way of thinking about them that we find most useful. Okay, so the first thing is to denote that the upper and lower transforms are in fact the envelope of quadratic functions with a fixed quadratic term. Okay, yes?
How sensitive is this that you use quadratic function? You could also take the absolute value to some power which is positive.
Yes, yes, this is true, but yes, and you can do that. You can do that, but using the quadratic power gives you some nice properties, some of which I'll sort of mention a bit later. But yes, you can do that. Yeah. So these, yeah. So the first characterization is this envelope of the quadratic functions with a fixed quadratic term in terms of the which is like the semi-convex or semi-concave envelope. Then one can also characterize them as so-called critical mixed Moreau envelopes, which are related to the ideas of inf and sup convolutions. And so here the lower transform, so first we do the m lower lambda and then m upper lambda, and then the upper one is when you do it the other way around. Okay? And then you can also characterize the lower and the upper transforms in terms of opening and closing morphological operators with a fixed quadratic structuring function, right? Where you have here your b lambda x is minus lambda x squared, and so then first of all you can characterize these Moreau envelopes in terms of the so-called erosion and dilation, and then when you do it twice you get these opening and closing operators. Okay, so these are alternative characterizations of what I'm talking about. And so now let me show you what they actually do in a simple case. Okay, so first of all, so here my function is just going to be sine of x, right? So it is -1 when x is negative, and it is +1 when x is positive. So this red thing is just the graph of my original function. Okay, and then we just build up gradually what the lower transform actually is. Okay, so we start with f, and then we add on lambda x squared, and so when we do that, we get this blue curve, right? And so it is simply like a quadratic function, but it's lower on one side than it is on the other side because of the presence of the sign. Then we want to take the convex envelope of this function. And okay, so what's it going to be? You're basically going to get the original curve on this side and the original curve up here, but then you have a bit here where the original function is not convex. And so when you take the convex envelope, you get the green curve, right? Which is identically equal here, identically equal up here, and in between you just get a straight line which is tangent to the blue curve, right? So this is the convex envelope. And then of course we have to subtract off the lambda x squared again. Right? And when you take off the lambda x squared, you get the black thing. And so if I now take away the working, I am left with this, right? So the red thing is what I started with, and the black thing is the lower compensated convex transform. And there are two things to note. So the first one is that the black curve lies underneath the red curve, right? And in fact, this is true more generally. And this is why it's called the lower transform, right? It's from underneath. And then the second property, which is very important for our applications, is that the black curve is identically equal to the red curve, except close to the point at which you have a jump in the red curve, right? Okay, so I will, and then this also happens more generally, but I'll mention that later. Okay, so this is what we have for the lower transform. So then let me basically do something similar for the upper transform, just to show you how it works. So again, we take f, again, to be sine of x, so -1 and +1. And then we build up what we have from the upper transform. So, so what do I do? So I take sine of x, and then now we build lambda x squared minus f of x. Right, so again we have the quadratic function, but we have a discontinuity at 0, right, which is the other way around from the way it was before. And then we take the convex envelope, so now we have our straight line on the left hand side instead of on the right hand side. And then I take away well, I don't take away, I take lambda x squared minus the convex envelope, and now I get this black curve, right? And so what is this? So now I take away the working, and so I have the same red one to start with, and now my black curve looks like this. So in particular, it lies above the one that I started with, right? Hence the name upper transform. And in addition, it is identically equal to the original function, except close to the point at which you have a singularity, right? Sorry?
It's
Yes, this one is Lipschitz. Yes, 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 indeed. Okay, so these are the sort of basic examples. And then let me, before I sort of give a list of general properties, let me just illustrate the role of the parameter lambda, right? So in the pictures that I've just drawn, it was just for a fixed lambda, but what happens as we change lambda? And what happens is the following. So this is my original sine function. And okay, so here's a lower transform with lambda is 0.1. But then as we increase lambda, it basically becomes closer and closer to the red function, right? So this is basically what happens, and this distance here is 1 over the square root of lambda, right? So as you increase lambda, it gets closer and closer and closer, and so the size of the set on which the original function is different from the transform is tending to 0 as lambda is tending to infinity, right? So the size of the set where they are the same is getting larger and larger and larger. Okay, so these simple examples give you a feel for what's going on. And so here are, okay, I've forgotten about this, so I put one more example. So that was just a sine function. But here's an example which is more related to what I'm about to say about the medial axis. So let me talk about this one also. So here we have our function, and now it is the square distance function to the 2-point set -1 and 1. Okay? And so in this case, the original function, so on the left-hand side, so this is just the original function f. On the left-hand side of 0, you just get this quadratic function, and on the right-hand side, you get this one. Okay? And so here we have a singularity, but it's of a different type. It's not in the function itself, but you have a discontinuity in the derivative at the point 0, right? And so in this case, if you add on lambda x squared, then you get this object, right? Now, when you take the convex envelope, you just get a little straight line across the bottom here. And then when you take off the lambda x squared, you get this object, right? So again, this is the lower transform, so it's lying underneath. And it is smoothing off in a neighborhood of the point where you have the discontinuity in the derivative. Okay? Okay, so now these examples illustrate some properties that hold more generally. And so in particular, so here is just a sort of potted list of them. So first of all, the lower transform is always less than or equal to the function, which is less than or equal to the upper transform. Secondly, if you have an ordering of the functions, then the lower transform of f is less than or equal to the lower transform of g, likewise for the upper transform. These properties are not hard to show. There is a relationship between the upper transform of f and the lower transform of minus f, which just comes from the way that things are defined. Then we have a very important property, this translation invariance, right? So this is to do with the fact that if you take this quadratic function, so in the examples that I showed, the quadratic function was actually centered at the point where there was the singularity, right? But this actually doesn't matter, right? Because if you center the quadratic function at a different point, you still get the same answer, right? And the reason for this is simply coming from the fact that if you center the quadratic function at a different point, then in this function in here, you're just adding on an affine function. When you take the convex envelope, that just adds something onto the convex envelope, which then cancels out with the bit that you have here, right? So it doesn't matter where you put it, you get the same answer. So in a sense, you don't need to know where the singularity is in advance. It will still be detected. Okay, other properties. So this is just a sort of basic stability property that if two functions are L infinity close, then the transforms, that should also be a lambda, I forgot, sorry. the transforms will also be L infinity close. And then you get various kinds of regularity properties, right? So I won't say too much about this here, but because I'm going to be interested in square distance functions, let me just mention here that the lower transform of the square distance to a closed set is in fact a C11 function. And then you also get, so you can also get that if you take two of these transforms, so a lower then an upper or the other way around, then again you get a C11 function. So again you get some regularizing properties which come from these transforms. Okay. Then there are two, so those are basic properties and they are important, but there are two properties which are extremely important for applications, and they are the following. So the first one is a locality property, right? And so here I'll state it for the square distance function because this is what we're going to be particularly working with, but locality properties hold in general. And so the property is the following. So if I take a non-empty closed set and some point in Rn, then the lower transform of the squared distance function to the set K at the point x0 only depends on the values of the original function in a neighborhood of the point x0. Right? So this is just, there are different ways of writing it. This is just one way of writing it. I'm just taking the function and multiplying it by the characteristic function of the ball centered at x0 of a certain radius. And here we can prove an estimate that says that you can take the radius to be 2 over lambda times the distance of x0 to the point k, to the set k. So in particular, first of all, the lower transform only depends on the original function close to the point x0, or in a neighborhood of the point x0. Moreover, the size of that neighborhood tends to 0 as lambda tends to infinity. And this is very important from the point of view of calculating, or in particular computing, the transform. Right? Although the convex envelope is a global object, right, in order to compute them, you only need to know about the original function in a neighborhood which we can quantify about the original point. So this is a locality property. And the second property is a tight approximation property. This is a completely different use of tight approximation from one of the talks yesterday afternoon. So here, by tight approximation, we just mean that, exactly as we saw for the prototype example, that the transform is identically equal to the original function except close to the singularity. It's not approximately equal, it is identically equal except close to the singularity. And so a more general statement is the following, that for every point x0 at which the original function is C11, is C11 in a neighborhood of x0, then the lower transform and the upper transform will be identically equal to the original function when lambda is sufficiently large. Right? And we saw this for the prototype, right? It was identically equal. Okay, so this is basically what we're about to use, but before I do that, let me show you a couple of quick examples. So here we're just taking a 4-point set in R2. And so here our set K, so here I'm working with the distance squared to the set K. K is just the set consisting of A, B, A minus B, etc. So just the 4 points on the vertices of the rectangle. And the picture on the left-hand side is just the graph of the square distance function to the set K in the particular choice where A is 2 and B is 1. Okay? And then the thing that you get on the right-hand side is a graph of the lower transform of this function f, so of this square distance to the set K, for a particular value of lambda. Right? So this is like a 2-dimensional example corresponding to the one that I showed earlier in 1 dimensions. And what you can see here, obviously you can't see it quantitatively, but qualitatively, hopefully you are convinced that it looks the same, except close to the points where you had a discontinuity in the derivative. Right? And the points where you had a discontinuity in the derivative are smoothed off by having the lower transform. Right? Here's another example, just to sort of fix ideas. So here we are taking an open box in R2, so mod x less than a, mod x less than b, and then we'll take k to be the complement of this box. Right? So we start with, so this is our rectangle, and we're taking our set k to be the complement in R2 of this rectangle. And so then the thing sitting on the left-hand side is just the graph of the square distance function to the complement. And so you get this ridge forming in the middle of the box. Right? And then when you take the lower transform, it smooths off what's happening down these edges and along the top. Okay? Okay. And so the key idea is the following, right? That the tight approximation property allows you to detect singularities by taking the difference between the original function and one of the transforms. Right? This is the key idea. Right? So in particular, we can capture different kinds of singularities using the so-called, what we define to be the ridge and the valley transforms. So the first one is when you take the function minus the lower transform, and the second one when you take the function minus the upper transform. Right? So let me show you an example to see how this works in practice. So here we consider just a function defined on R2 to be mod x minus mod y. Right? So the graph of this function is the thing that's drawn here on the left-hand side. And it has two ridges. Well, no, it has one ridge and one valley, right? So you have a ridge here, right, coming from the mod x, and then the minus mod y is giving you this sharp valley going down in the two directions. And then if you take the lower transform, it smooths off the top ridge, but does nothing to the other one. And if you take the upper transform, then it smooths off this one and does nothing to that one. Right? And so then if we take some differences and do a little bit of scaling, then we get the following. So if we take the ridge, right, which is f minus the lower transform, and multiply by lambda for reasons to do with some scaling properties, then we get this object. Right? And this object acts as a detector of this part. Right? Whereas if we take the function and subtract off the upper transform, then we get precisely this object, right, which is acting as a marker for this part. Right? And so these are functioning as ways to detect certain kinds of singularity. Right? And so, okay, so then we have various properties that it's worth to mention just briefly. So first of all, why did I scale by lambda? So in the case where f is Lipschitz, which the example that I just showed was, then you can show that lambda times the ridge is always bounded by a constant depending on the Lipschitz constant. Likewise for the valley transform, and moreover, you get limiting properties as lambda tends to infinity, that not just do the ridges tend to 0, but if you multiply by lambda, you still get it tending to 0. Right? So basically, as lambda gets larger and larger and larger, the lower transform will get closer and closer and closer to the original function, right? And the difference will be different. Okay. And then, then let me briefly mention a few other properties. So then you have some affine invariance. So if you add on an affine function to f, then you get the same thing. Likewise with the valley transform. You get some scaling properties if you multiply f by alpha. And then you also get some stability under some curvature perturbation, right? So if you take your original function f and you add on a perturbation, a C11 perturbation g, where you have some control on the Lipschitz constant of the gradient of g, then you can estimate the ridge transform of f plus g corresponding to the parameter lambda in terms of the ridge transform of the original function with a slightly different value of lambda. Okay, so these are some basic properties, and using this idea of detecting singularities, we can, and now I'm making a lot of leaps, apply via a numerical implementation. We can apply these ideas to a large variety of applications in image processing, feature extraction, and shape interrogation, right? And here I'm just showing you some pictures, and then I'm going to talk about one of them more specifically. So the two on the left are medial axis, so I'll talk about that in more detail in a second. Here we are detecting the intersection between some surfaces. This is also an intersection problem. This is detecting areas of high oscillation. This is noise removal, and this is an interpolation from level sets of a given curve. And all of these things can be done using the ideas coming from the properties of the lower and the upper transforms that we were mentioning. Okay, so now let me talk in a bit more detail. So this is just to show you some of the big picture before I talk about something more specific. And so now I want to talk about the medial axis, right? And so first of all, I should tell you what this is. So here we will work with the following definition. So for a closed set K in Rn, the medial axis is defined to be the set of points in Rn such that the distance to the set K is attained at least 2 points, right? So here are three just prototype examples. So in these three examples, the medial axis is the white thing inside the black object, right? The set K can be thought of to be the complement of the black object outside the object, right? So if K is this region out here, then the white thing is the set of points inside the black shape where the distance to the boundary is the distance to the outside is attained in at least 2 points, right? So if you take a point here, then the point here and the point here are the same distance from this, right? Likewise with the hand and with the famous maple leaf, okay? And so the medial axis and its associated distance to the boundary give you some simplified representation of shapes, which has a lot of applications. For example, to character recognition, shape restoration, medical imaging, and various problems in computer-aided design. But it's well known to have serious stability problems, right? And to see that, we look at the following example. So here, I'm taking the rectangle, and the medial axis is just this set inside the rectangle. And the big problem is that if you put a little bump on the boundary, this generates an enormous bit of extra medial axis, right? So it's highly unstable with respect to small perturbations on the edge. And this is just showing that this is particularly problematic when you have a digital image where you have a staircasing effect on the boundary due to the pixels in the image. And then you get this kind of effect, right, where the fact that you have these bumps on the boundary give you all sorts of extra lines. Okay, so this gives you a simplified representation of the shape, but it's highly unstable to the behavior on the edges of the shape. And okay, so there are many ways of extracting the medial axis or an approximation to the medial axis, right? So one way is by skeletonization by thinning or Grassfire methods or some kind of discretization and approximation by Voronoi diagrams. But in none of these cases are there, or to our knowledge, are there good estimates of the stability of the process, and in particular, no proofs of so-called Hausdorff-stability of the method. And so what I want to do is to now introduce an alternative which exploits the properties of the compensated convex transforms, and we do get some Hausdorff-stability properties. Okay. And so what we do is we take the square distance function, right? So we take the square distance function from x to some set k. And okay, so this is the infimum of the absolute value of x minus y squared for y and k. And the medial axis is precisely the set of points at which this squared function is not differentiable. Okay, so this gives us a characterization of the medial axis in terms of a singularity set of some function, right? And you can probably guess what's coming next, because now we define a so-called multiscale medial axis map, so I'll describe why I call it multiscale in a moment, which is defined to be some scaling of the ridge transform of the square distance function, right? And so the ridge transform is just as we had before, the original function minus the lower transform, right? And this object turns out to have very good properties for detecting and analysing the medial axis. Okay, so this is what I'll now tell you about. So first of all, what kind of properties does this object have? So the first result is the following. So if I take a point which is in the complement of the closure of the medial axis, and I take lambda to be sufficiently large, right? So lambda multiplied by the distance of x to the medial axis is sufficiently large. So either lambda is large or we're a long way away from the medial axis. Then we get that this medial axis map is equal to 0. Right? So remember that the medial axis map was just a ridge transform, right? So the medial axis map being equal to 0 just says that the square distance is equal to the lower transform. Right? So this is what we would expect from the examples that we saw before, that when you're not close to the medial axis, then the two things will be equal, at least when lambda is large. And in fact, so this set depends on lambda. And so if we define V lambda k to be the set of points where lambda times the distance to the medial axis is less than or equal to the distance of x to k, then the intersection of these sets is just the closure of the medial axis. Right? And so what this is telling you is that for these points x, the medial axis map just gives you 0. And you can have a slightly different statement in the case where you have bounded domains. So here, if we look at the medial axis of the complement of the domain, and we have an estimate which now involves the diameter of the domain, then again we get that for lambda sufficiently large, we have that the medial axis map is 0. Okay, so this is telling us that when we are not close to the medial axis, then the medial axis map gives us 0. And this has some, so now I have a small digression, that this has some implications for the regularity of the square distance function. Okay, so it's well known, so the square distance function is interesting for a number of reasons. In particular, it's a viscosity solution of the modulus of grad squared u is equal to 4 times u. And it's well known that you cannot expect better regularity of the square distance function than C11.
What are the boundary conditions of the equation up there? So u must be 0 on the boundary, or
0 in k.
u square is 4u. What are the boundary assumptions?
U equals 0 in k.
Yes, sorry, u equals 0 in k.
Okay.
Okay, sorry, yes. And, okay, so here's an example. If we take k to just be this box, right, and we consider the square distance function to this square, right, then this is an example that shows you that you should not expect better than C11 regularity, right, because if you look at the square distance function to this square, right, then you don't get C2 regularity, because you see here that the distance, if you're on the left-hand side, you just have x squared, here you have y squared, and here you have x squared plus y squared, right? So this is not a C2 function. And this is just a graph of the square distance function. And there are some local regularity results, for example, and results due to Albano in 2014. But the moral of the story is just that we can get some information about the regularity of the square distance function using the regularity of the lower transform. Right? So it's known that the lower transform is a C11 function. Moreover, that you have a bound on the Lipschitz constant of the gradient of the lower transform by twice the maximum of 1 and lambda. Right? And in fact, that this lower transform is a C11 subsolution of this problem. And so this gives you a result about regularity of the square distance function away from these sets V lambda k, right? Simply because the square distance function is equal to the lower transform on these sets, right? And so you basically get that it's C11 away from these sets. You also get a bound on the Lipschitz constant. And so let me just show you a quick example of that. So this is just in the case when n is equal to 1. So here we take k to be the union of the set between minus infinity, minus 1, and 1 infinity. So in this case, the medial axis is just 0, right? So we're just looking at a one-dimensional problem. And the square distance function is equal to the lower transform precisely when mod x is bigger than or equal to 1 over 1 plus lambda. So on this part and on this part. And if you do the calculation, then you see that the difference in the gradient of the square distance function at the point x plus, so this is this touching point here, and the point x minus, which is this point here, is precisely 2 lambda times the absolute value of x plus and x minus, right? And this shows you that, okay, this is an illustration of the result, that this lower transform is giving you this good approximation, it's giving you regularity outside, and this bound is sharp, right? In the sense that the Lipschitz estimate for the gradient of the square distance function fails on all open sets which contain this set. So if you try to take it any bigger, then the distance function, you would have a larger difference in the gradient. Okay, so this is sort of a corollary that you get information about the square distance function regularity from that for the lower transform. But now let me come back to the medial axis map. And so, okay, so what we saw was that the medial axis map is 0 when you are away from the medial axis, right? When you are sufficiently far away from the medial axis or when lambda is sufficiently large. But to get a bit more information, we introduced this concept called the medial axis landscape map. And, okay, so to define this, given a point x in Rn, we will let kx be the point y in the set k at which the distance to the set k is attained, right? So if we are in the medial axis, then the set k of x contains at least 2 points. If we're not in the medial axis, then it contains a single point, right? So this is just the set of points in k at which the distance to the set k is attained, right? And then we define the medial axis landscape map of k in the following way. So we take the squared distance of x from k, and then we subtract off the square distance of x from the convex hull of k of x, right? So k of x is now a subset of Rn, right? And so now this denotes the convex hull of that set, right? And this quantity, it turns out, characterizes the medial axis in the sense that it is strictly positive on the medial axis and it is 0 everywhere else, right? So this quantity, so I'll justify that in a moment. So why is this? So if we take a point which is not in the medial axis, then this set k of x is just a single point by definition of the medial axis, right? And then we get that the convex hull of k of x, well, is just k of x. It's a single point, right? And therefore, the medial axis landscape map is just 0, right? Because if you go back to the definition, it's just the square distance to k minus the square distance to the convex hull of k of x, but this is just k of x, right? Okay, so that's why it's 0 when you're not in the medial axis. And if you are in the medial axis, then there are 2 points in k of x by definition, y1 and y2, which tells you that their average is in the convex hull of k of x, right? And then, if you do the calculation, then the square distance from x to k can be written as this first term, so this is just a slightly exotic writing, right? And then this thing has to be greater than or equal to the distance to the convex hull of k of x, because this object is in the convex hull of k of x, right? And then you do the calculation and you get this, which is strictly positive because y1 is not equal to y2. Okay? So this quantity completely characterizes the medial axis. And you might ask, well, why don't we use this instead? Right?
If you touch at 3 points,
yes,
that are the singular points of the medial axis.
Yes.
Can you also find them out?
What do you mean, sorry?
I mean, if the sphere touches at 3 points,
Yes.
this is where the medial axis splits.
Yes.
Can you find that out?
So you can find it as the intersection of different parts of the medial axis. Yes. Yes. So this is a very useful object, right? But it's not so easy to compute directly because of the presence of this k of x, right? Because you need to know to compute this the points at which the distance to the set is attained, right? But it is very useful nonetheless because there's a key interaction with our medial axis landscape map, right? And so there are two properties. So one is you get lambda independent bounds. So if you take something in the medial axis map, if you take something in the medial axis, then the medial axis landscape map has to be positive. This turns out to be a lower bound for the medial axis map with value lambda, which is also bounded above. And if you take the limit as lambda tends to infinity, the medial axis landscape map, which we can compute using the computation of the lower transform, converges to this medial axis landscape map. Right? So you get a complete characterization of what happens to these maps in the limit, and you get some stability properties. So I'm glad I got this far because I wanted to tell you this part. So to illustrate the stability properties, then let me just take a simple example. Right? So here I'm going to work in R2, and then I take my set K to be the 2 points minus alpha 0 and alpha 0. So 2 points on either side of the y-axis. Right? So in this case, the medial axis is just the y-axis. Right? The medial axis is just the y-axis, and I think the green is a bit hard to see, but you get a formula for the medial axis landscape map, which is 0 if mod x is greater than or equal to alpha over 1 plus lambda, and it's some other formula when you are close to the medial axis. Right? In particular, if you look on the medial axis, then x is 0, right? And then, so this is just 0, the 1 plus lambda squared cancels with this 1 plus lambda squared, and you are just left with alpha squared. Right? And the moral of the story is that if alpha is small, these 2 points are close together, and you get a low height for m lambda, you just get alpha squared. Whereas if they are far apart, then alpha is larger, and you get a higher height. And this is very important from the point of view of stability, because it allows us to select different parts of the medial axis depending on the distance between the points that generate a given part of the medial axis. So what we get, so here's a couple of examples. So here we just take again a 4-point set, which are the 4 points on the edges of the rectangle. Right? And then we compute the medial axis map for different values of lambda. Right? So the medial axis map is just a scaling of the difference between the square distance function and the lower transform of the square distance function. And so for some relatively low value of lambda, you get something that looks like this. So you can see here that you get a peak at the point of the intersection between the two bits of the medial axis. And in particular, right, so the bit here is generated by these points which are far apart, right? Whereas the bit in the middle is generated by these points which are closer together. And so this part is higher and this part is lower, right? Which you can use as a way to select the different parts of the medial axis. And then the other pictures, they just illustrate the role of increasing lambda, right? So as lambda increases, it gets flatter and flatter and flatter, right? And so it's getting closer and closer and closer to just having two markers, one in this direction, which is higher because it's generated by these points, and one in this direction, which is lower because it's generated by these points. Okay, and here's another example. So in this case, you just have 5 points, 1, 2, 3, 4, 5. They are the set K. And in that case, the medial axis consists of these 4 lines. And then if you compute the medial axis map, then you get this nice colored picture And you can see that probably can't see this one, but there is actually a very faint line drawing there. You get 4 different heights, which correspond to the fact that these points are far apart, closer, closer, and even closer, right? And this is very important from the point of view of if you have a little perturbation on the boundary, which is giving you a big extra bit of the medial axis, this is typically generated by points that are close together, and so it gives you a very low height, which you can just chop off by thresholding the function, right? Okay, and here's some other sort of related examples. So here we have some points which are sitting along 2 vertical lines. And the motivation for this example is that you are often interested in extracting information when the original object that you have is expressed as a point cloud, right? So instead of having total information about your shape, you are just representing the shape by a collection of points on the shape, right? And then what happens is that, so these dots are the set K, right? And then if you calculate the medial axis map, you get a high bit in the middle, which is coming from the fact that you have the straight line in between the 2 sets of points. And then you have these little low bits, which are coming from the fact that you have these gaps in between the points, right? And this is just a different example where these points are closer together, right? And so in this case, you can threshold out the effect of having only taken a selection of points on the boundary, because the bit in the middle has a higher height. And in fact, one can prove, as I advertised at the beginning, Hausdorff-stability properties in the following sense. So if we take 2 compact sets and we define the Hausdorff distance in between the sets in the usual way, then if we take some bounded set in Rn, then there is some constant C that depends on this set, such that the difference in the sup norm between the medial axis maps corresponding to K and L is bounded above by a constant times the Hausdorff distance between the sets. And so this gives us a very strong stability property that allows us to extract information from point clouds representing objects. Okay, so now I think I should be quite close to finishing, which is fine because I just want to show you some pictures. So this was one of the first examples that we did, and this is, what is the Chinese character? Okay, so this was one of our original examples, and you can see it's very obvious here that you get this fishbone effect, right? So here we have the black object, and when we compute okay, you mean to choose the Chinese character? Yeah. Okay. So this is you compute the medial axis of this object, and you get this fishbone effect. And the fishbone effect, right? So you're basically getting the bit in the middle, and you're getting all these little bits going to the boundary because of the fact that you have the digital representation of the object. But then, if you do this thresholding effect, then you get the bit in the middle, right? Which is what you hoped for. Right, which you just get by only looking at the values of this map m lambda, which are greater than a certain quantity. Yes?
Well, that would mean Hermitage retreat.
Say again?
Hermitage. That's the symbol there.
Ah, okay.
Yes.
Okay, thank you. Okay, I don't know how you did that, but anyway. Yes, okay, so this is just when you select it by some thresholding procedure. And there is another way that you can get it, which is sometimes useful, which is that if you originally took a larger value of lambda, right, then that's another way of selecting just the middle part, right? So this looks very like the previous one, but it's obtained in a different way, right? This is when lambda is equal to 5, and the previous one was when lambda was 0.1, okay? And then the thing on the right-hand side is a regeneration of the original symbol using the medial axis, right? Okay, so this is a few examples. Then, okay, this one just looks fancy. So this is a dog lung, right? This is a cast of a dog lung, and this is the medial axis, and this was one of the very early examples we did, and it was nice because it's just as fast as doing a, Chinese character, right? You don't need to know anything a priori about the complexity of the object. It's simply an image, right? And so this is the medial axis in this case, and this is thresholded to take only some of the most important values. So this one, I sort of chickened out. I did have a movie, but I didn't put it in because the file was too big, basically. But we did actually have 20 different ones where you basically compute the medial axis. So this is the maple leaf, and you get lots of little branches because of the behavior on the boundary, but then as you increase the threshold, you only get the most important parts. And then you see, so this is really a black leaf with the medial axis, but it turns out that the medial axis looks very like where the veins would normally be on a leaf, which is probably because the leaf is quite intelligent, right? But this is okay. So this is just to illustrate the fact that you're increasing the threshold and you're picking out the main parts of the medial axis. You look as if you have a question.
Could you find out the capillaries inside the leaf, maybe by making the lambda larger or smaller if you go to the boundary, because there you have more capillaries?
Well, possibly. I mean, maybe that's what you're seeing here.
Yeah, or the arteries in the lung. I mean, it could be.
Possibly. Yeah. Okay, and this is an example that illustrates the stability. And so here, this is our original domain, right? And okay, so the one on the left, we take the original domain is the white bit, and the medial axis is just the white lines inside. And the thing on the right-hand side, you possibly can see there are just some white dots here. And the white dots are simply, they are quite sparse, but they are a sampling of this white region, right? So this is like taking this white region and representing it as a point cloud, right? And then when you try and generate the medial axis from this point cloud, you get something which is pretty good, right? In spite of the fact that you're only taking this point cloud information roundabout. Okay, so this is an illustration of the stability. And then I also wanted to give at least one three-dimensional example. So here we have two spheres which are intersecting, and the boundary of the sphere again is sampled, so that's why it looks all blobby, right? And so the true medial axis of the two spheres in that case is just a straight line between the center of the spheres. And the blue thing that's shown here is just what's generated automatically as the medial axis from the fact that we have the sampling of the boundary of the sphere. And that is more or less what I wanted to say. So there are some papers here, and the one I talked about today is mainly this one in the middle, where we're talking about the medial axis. But then there are some other ones where, okay, this is the original work of Kewei at the top, and then we have some other ones to do with extraction of different kinds of singularities and some kind of interpolation things. We even eventually, after many years, managed to get a patent. But it took a very, very long time. And so I want to finish by thanking your attention, and also I come from Swansea, and near Swansea there is a very beautiful area called Gower, and there's a very famous beach called Rosslea, and at the edge of Rosslea there's a very distinctive geographical feature which is called Worm's Head. And this is Worm's Head, and some years ago when Kewei was still in Swansea, we went there with a visitor, and at that time we noted that it looked very like a square distance function to the edge of the thing. And so I just want to finish with that and to thank you for your attention.
So can you apply this kind of technique to images with a kind of a noise?
So I couldn't see who was asking the question.
So if in the Chinese character word, we do have put some noise, or for the maple leaf, we put some noise, can you also get the stability?
Yes, we can, I mean, so one thing I didn't show, but I did show briefly in the in the sort of advert in the middle about different things that we can do is that there are some things where you get good properties about removing noise from things.
The first remove noise.
From removing noise. So if you add some noise, then, okay, so it's pretty good at removing salt and pepper noise, right? So white or black noise. Grayscale noise of different types is harder, but the fact that we have the stability properties gives us some results in that case.
Maybe the same question in a different way. You didn't show it, but can you describe what happens when, you know, the maple leaf boundary becomes wrinkly? Does it work fine?
I think it is wrinkly.
You know, again, more artificial noise sort of applied all around the boundary.
So we didn't do that explicitly, but somehow implicitly it already is wrinkly because of its digitalization. And so somehow that's exactly what's giving you this very, in one of the examples, whichever one it was. Yeah, it's the one on the top left is pretty bad close to the boundary, right? I mean, it's giving you quite a lot of stuff. Yeah.
So what about the computational complexity when you go to higher dimensions? Because it's if you'd like to do the same but for data which are in higher dimensions.
So the issue is to do with computing the convex envelope. As far as I know, Antonio, you can correct me, did we do anything higher than 3 dimensions?
Yeah, it's the convex envelope, but it's local because of the lambda,
Yeah, because of the locality
it's not
property.
the convex envelope of all the function, that would be NP.
But
because of the lambda, then it's localized.
But how the lambda evolves when you go to higher? Does it depend on the dimension or no?
It depends on the size of the box that you are considering. That is
So because you have this
linear with
object.
that, the size of the box. Elaine is considering, yeah. Are you convinced?
Yes.
Yeah,
Thank you.
Yeah, it's and there is the convex envelope, but because of lambda, also because of the first example there, you saw that the effect is only local. It's 1 over square of lambda there, and then the algorithm depends on the size because we have an algorithm that is through the Muro envelope.
That is what?
Through the Muro.
These things are mostly for shapes in lower dimension. That means the dimension is not a million or something to look for shapes. It's the Euclidean shape. This is more or less the place where the medial axis is defined. You try to analyze geometric shapes, so the dimension is low. Therefore, the dimension is not a big thing in the computational. The higher, of course, the lower, but it's not an NP hard question, for example. It's rather depending on the dimension of the box. This is for digitalized thing.
Even in 3 dimensions, the medial axis consists of 2-dimensional. It's more a medial scaffolding. So it always has only 1 dimension lower than your surrounding space.
Yeah, but you could try to apply the same method.
Yes, it works.
It's the matter of the computation blindly for the lower transform. That's all. That has nothing to do with the particular geometry the set contains. You just run the lower transform, essentially. That's give you the answer.
And so you have some code available to do that? Where is it?
We have a code, yes, it's MATLAB. This is just run MATLAB.
But is it really available on the web?
No, it's not.
No, it's patented.
Yes.
Patented.
not
Ah,
There's a free
There is a
version.
patent.
You have to pay.
But it's yeah.
Any further questions? Then it's coffee time. We come back in half an hour. 11:35.